Say, I know what to do.
What to do?
What you doing? Show 'em.
I'll wait with
You're
doggy.
gonna select the dog and then click on it. Very good. Doggy skating up and down the ramp.
I'm not falling.
No, he's on a skateboard and he has very good balance. Wow, smart you are. Okay, what are you doing? You're gonna select the girl. There we go. Arman is doing a PhD simulation. Say hi. Say, I know what to do. Good day again, everybody. Today we're going to look at energy, more specifically mechanical energy. But to ask the question, what is energy? Well, energy is actually the ability to do work. What is work? Well, we'll get to that a little bit later. Now, energy follows a specific law. It is actually called the law of conservation of energy. Now, what is the law of conservation of energy? It states that energy cannot be created or destroyed, but it can change from one form to another. What does that mean? Well, we can't create energy, but we can harness it. We can't destroy it, but of course we can allow it to change from one form to another. With the aid of a PHET simulation displayed at the beginning of the video, we are going to look at mechanical energy. But what is mechanical energy? Well, it is a sum of two specific types of energy: kinetic and potential energy. To further understand it, let's break down what mechanical energy really is. To do that, let's understand first what kinetic energy is. Kinetic energy is described as the energy that a body possesses due to its motion or movement. So, once a body moves or once an object moves, it possesses kinetic energy. Kinetic energy is given as a half mv squared, where m refers to the mass of the object, and v refers to the velocity of the object. So it's important for us to note that if an object has a specific velocity, it will therefore have kinetic energy. What does it also mean? If we increase our velocity, we can increase our kinetic energy. From this equation, kinetic energy is directly proportional to v squared. So the faster an object moves, the more kinetic energy it has. The slower an object moves, the less kinetic energy it has. Consider a car, for example, that moves in a specific direction, therefore having a specific velocity. Well, the faster our car moves, the greater the kinetic energy of that object. The slower the car moves, the lesser the kinetic energy of that object. Now let's look at potential energy. Potential energy is known as stored energy, and there are many different types. For example, chemical energy, which comes from batteries and fires, elastic energy, any elastic material, and gravitational potential energy, which of course we're going to look at more specifically. What is gravitational potential energy? Well, gravitational potential energy is described as the energy a body possesses due to its state or position. Its state really refers to whether it's stationary or not, and its position has to do with its height. So what does that mean? An object that is stationary has the potential to move, therefore it has maximum potential energy, while an object suspended or positioned at a height has potential energy. Now, gravitational potential energy is given as mg by change in height, m being the mass of the object, g being the gravitational field strength, and change in height, or delta h, is the change or difference in the height of an object from a point. Now, what's important about this is that m, mass, is constant, g, gravitational field strength, is constant. So what does gravitational potential energy depend on? Well, it's directly proportional to that change in height. What does that mean? As height increases, the gravitational potential energy increases. So the higher we go on a mountain, for example, that gravitational potential energy increases. However, the lower we go, or as the height decreases, the gravitational potential energy decreases. An important point to remember is that ground is normally a position where height is taken as 0. So going upward means that we increase in height, and therefore gravitational potential energy. Let's consider a diver jumping or diving off a high board at a height h from that horizontal surface, which is the surface of the water. At that surface, height is considered to be 0. Where the diver stands, his height is considered to be that maximum height, awaiting, of course, to jump into the water. At this maximum height, we can say that he has maximum gravitational potential energy, since, of course, that value of energy is directly proportional to the change in height, taken from that horizontal surface, h equals 0. At that minimum height, his gravitational potential energy is minimum, or 0. Well, what does that tell us about velocity? At the very top, velocity is 0, so his kinetic energy, which depends on velocity, is also equal to 0. However, just before impact with that water, he is moving the fastest. So at that point, just before impact, his velocity is maximum, making therefore his kinetic energy at the very bottom maximum. Now, let's consider halfway along that jump. Halfway along that jump, his height is actually divided by 2. He has half its maximum height. What does that mean? He will therefore have half his maximum gravitational potential energy. But he is also moving at half his maximum velocity. So his kinetic energy is also divided by 2. His maximum kinetic energy, that is. Now, since mechanical energy is the sum of kinetic and gravitational potential energy, well, at the very top of this highboard, this diver has maximum gravitational potential energy, but minimum kinetic energy, meaning 0 kinetic energy. Bottom, however, the situation is the opposite. The diver has maximum kinetic energy, but minimum or 0 gravitational potential energy. Midway along his dive, well, the diver has gravitational potential energy and kinetic energy that are equal to each other. What does this mean? Well, it gives us a clear indication that mechanical energy of any object or any moving body is always constant. This keeps in line with the law of conservation of energy, which tells us that we can't create or destroy energy but allow it to change from one form to another. So as the kinetic energy increases, the gravitational potential energy decreases. Of course, once air resistance is not considered. And of course, mechanical energy is therefore, we say, conserved or constant. What does that relate to? Well, like the biceps and triceps of our bodies. When we contract our bicep muscles, well, our triceps become relaxed, and vice versa. Now, let's consider an object that is dropped from a height, rather than allowed to slide down an inclined plane. Now, for simplicity, let me explain. An inclined plane, also known as a slope, is any surface that forms an angle to the horizontal or a horizontal surface. Now, in our example, this block or this object is not allowed to touch any side or any vertical height of the slope. Well, let's consider this vertical height as 20 meters. This means that at the very bottom, or the ground, height is 0. But at the very top, height is considered to be maximum, which is 20 meters. We are asked to calculate the gravitational potential energy at the top, point E, and the kinetic energy at the bottom, point B. Also, if the object was actually slid down that plane or slope to hit point C, we were also asked to comment on what will happen to this object in terms of its energy. Well, let's begin. Well, to begin with, our gravitational potential energy is given by our formula mgh, or delta H, where m is our mass given as 15 kilograms, g is 10 meters per second squared, our gravitational acceleration for an object that is moving at the pull of gravity, influenced of course by the pull of gravity, and our delta H, or change in height, is 20. We therefore get our gravitational potential energy at the very top of this inclined plane as 3000 joules. Well, what is going to happen to the kinetic energy at the very bottom? Well, considering that the object is actually not allowed to touch the slope at all, or any surface, and of course ignoring any resistance, just before impact, this kinetic energy should be its largest value, meaning that the object is actually moving the fastest just before impact. What does that mean? Well, the gravitational potential energy at the very top equals the kinetic energy at the bottom just before impact, making that also 3000 joules. Now, to answer the last part of our question, if the object is actually allowed to slide along the slope itself, well, the kinetic energy is not going to be the same as it was at point B. Why is that so? Well, if the plane is actually a rough plane, meaning that friction plays a part in slowing down this object, well, if it's slowing down an object, heat energy is produced, which means some of that kinetic energy is going to be transferred to heat energy. May not be a lot, but it still accounts for it. So that kinetic energy at point C will not be the same as the kinetic energy at point B once that object is allowed to slide down the slope. Let's take another example. A simple pendulum. At its points of release, we say that this object or this pendulum has a maximum height, whereas as it crosses its lowest point, we say that that height is actually 0. Well, at maximum height, don't forget that the gravitational potential energy is also maximum. At minimum height, as shown, the gravitational potential energy is considered to be 0. However, the object passes here at its maximum speed, making its kinetic energy maximum at that point. At our height being our maximum value, kinetic energy is minimum. If we consider an object or a skater going up and down a slope, the same principle is applied. At its lowest point, or the valley of the slope, the object travels its fastest. However, this is its height where it's 0. So at that point, kinetic energy is maximum, but gravitational potential energy is minimum. And vice versa. At the very peak of the slope, you have maximum height and therefore maximum gravitational potential energy. but the object slows down. Take considering, of course, this PHET simulation. Look carefully at the speedometer. Let's look at it in slow motion. When the object actually hits the lowest of one of the lowest heights, the speed is considered to be maximum. However, at its maximum height, one of the maximum heights, the speed is dropping. Again, minimum height, speed is maximum. Maximum height, speed is minimum. This tells us everything that we need to know about our gravitational potential energy and therefore our kinetic energy, which depends on height and velocity respectively. Let's take one more look.
It's so cute.
You're so cute. Mwah. You're going up and down the ramp.
Go that.
Yeah. So it's too steep. So you're gonna bring him this way. Wait. Stop. 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 Someone stop. Stop it. You're making it a little too high. How are you gonna go through that? Oh my gosh.